Welcome to another Würth Elektronik ISIS webinar. My name is Eleni Stark and I will moderate this webinar today. We are very pleased that you took the time to participate in our today's webinar. The topic today will be a practical guide to EMI shielding of electronic devices. Our speaker is our product manager, Antonio Alcaria. He will hold today's webinar and also answer your questions. Before we start with the presentation of our webinar, we would like to point out one thing. You'll be muted during this webinar today. This means that you can't ask us questions via microphone. Nevertheless, you have the opportunity to ask us all your questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us by yourself at isis-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email several days after the webinar. You can also watch the recording of today's webinar a few days later on our website under the navigation point webinars or on our Würth Elektronik YouTube channel. Now I will hand over to our speaker Antonio Alcaria and I wish you an exciting webinar.
So hi everyone, thank you Eleni for the introduction. We will start right away with this small webinar, Practical Guide to EMI Shielding on Electronic Devices. I'm Antonio Alcaria. As Eleni said, this is the agenda, and or we'll have a short introduction about what is shielding, then basics explanations about the main concepts I think you need to know about shielding. Then we have shielding apertures, and finally shielding solutions, how to solve these issues in nowadays electronic devices. About the introduction, what does electromagnetic shielding mean? To place it, basically it means to place a shield between some kind of noise source and a victim. This could mean like shielding your device from external noises or avoiding your device or preventing your device of interfering with another devices that are close to it. This is a really important topic nowadays due to the EMC compliance and the compliance test every device has to pass to be able to get the market. About the basics, electromagnetic fields are radiated from and received by conductive structures. Possible antennas can be cables, interfaces, apertures, traces, ground planes, bias slits, and components such as heatsinks, integrated circuits. At the end, every part that is conductive on a device can be an antenna. This depends on the size, as we will see later, and also on the structure and geometry. The relation between the frequency and the wavelength of an antenna is given by this formula. Like here you can see on the right, that is related with the speed of light. Some examples about frequencies and the wavelengths related to them are these ones. For example, this is the main frequency for Wi-Fi connections, and we can see that the wavelength is about 12.5 centimeters. Here in this graph, we can see a main overview of all the frequencies until 2 gigas, more or less. As you can see, the wavelength decreases at the same time as the frequency increases in a linear way. What is a half wavelength dipole? We have to understand that every conductive structure is not a proper antenna. It can be an antenna, but it cannot be the optimal antenna. The relation between this structure dimension and the wavelength is crucial. If we take in account distances that are close to half of the wavelength, then these points are the critical ones to emit and receive radiation, because they become like really good dipole antennas. Therefore, they're really sensible to signals. Also, it's important to have in account that we can like we can have an half wave antenna, and then this will be the optimal one until we get 1/20th of the wavelength, when the antenna is becoming like really worse and the effect of the antenna is really bad. As we said, this was the dipole antenna. This is the theory under it. And this is is composed by two parts. And then we have the potential power difference between these two parts. This changing field is creating an electromagnetic wave. This electric dipole, as it is called, or Hertzian dipole, creates electric field. We have a current changing between the poles of this antenna, and charges are accumulated at the ends. A second elementary antenna is created by a current loop, or it is called also magnetic dipole. Its radius is small compared to the wavelength considered. It's basically an ellipse or a circumference, and you can check it also with a normal cable if you put it on a loop. This creates a magnetic dipole and is able to create or to receive very efficiently magnetic field. The characteristic wave impedance is equal to the relation of the electric field strength to the magnetic field strength as a distance r from the antenna. This is the relation and the main impedance we can calculate from the wave. In the near field, here we have the formula. As we can see, the main difference between the electric and magnetic field is that the pi is moved from the numerator to the denominator, and the factor for far field wave impedance can be calculated as this one. This is also called the free space characteristic wave impedance. From an EMC perspective, most of the relevant noises sources can be described by one of the elementary dipoles. So either if we can check antennas, we can see electric dipoles or magnetic dipoles. In this graph, we can see how the wavelength is related with the impedance of the wave. As we are getting higher in the wavelength, then we are becoming closer to the far field, and for the near field, we are taking in account smaller wavelengths. This is the transition distance between near field and far field for both electric dipoles or electric fields and magnetic fields. It's really easy to shield electric fields. Normally, electric fields can start and end on charges. So basically, what we have to do when we have two metal surfaces, one close to the other, we have a difference of potential, we need to isolate these two surfaces. We have two ways of achieving this. Either we can have really good isolation between them, or we have, and this is the most common way, to have we have a very low impedance between these two. If we have a very low impedance between these two surfaces, we're achieving that the electric field doesn't have a difference of potential, so we don't have two charges. We have a very good connection between these two surfaces, and then we avoid the antenna effect of this geometry. So we said we need to achieve that the transfer is complete, so we don't have a difference of potential. On magnetic fields, it is a bit more difficult. The main solutions can be divided in the following. So on low frequencies and static fields, we have normally we use high permeable materials. Against medium frequency fields, we have use normally a skin effect. And on high frequency fields, we have reflection and absorption. This is depending of the materials we use, as we will see afterwards. High permeable materials are used for shielding of static and low frequency fields, as we said. The shielding effect is more efficient because it is closer to the source. The higher the permeability, the thicker the shield. The thickness of the shield we are placing has a very big influence, and the smaller the shielded volume. So some examples of materials and their permeabilities can be seen here, from nickel of 100 until mu metal that has about 25,000. This is a graph of calculation of the attenuation that you can achieve depending of the material. So we have copper and aluminum. We divided the graph into reflection and absorption ability. Also here we have the total. We'll see later that this is called, this is related with the permeability, two parts of the permeability. So as we can see, here is a quick reference guide of, depending of the material, which is the importance of the using of this material and how it changes. For example, we can see that copper is more effective, is starting to be effective at high frequencies, while aluminum is effective at very low frequencies. So we go now to shielding apertures. There is no perfect shield. This means normally you have an enclosure on your device, and you try with this enclosure to keep all the external noises away and to keep all the radiation that could be coming from your device from going to the outside. This is ideally, but at the end we need ventilation for heat transfer. We need also connections with cables. We need apertures for buttons, displays. So all these apertures are mining the shielding effectiveness of our device and our enclosure. There is a greater impact of apertures in the shield on the magnetic shielding attenuation than on the electric one. For higher frequencies, the decrease in shielding effectiveness due to leakage is more significant than theoretical shielding attenuation of a material. This means that it's really easy if you know how to shield these cases, and also we have to take in account always the frequency we are working on, the frequency of our noises, and the frequency of that in which our device is working. The maximum linear dimension of an aperture is crucial, not the area. Why? Because this is directly related with the theory of antennas we were explaining before. These distances can be considered as dipole antennas. And these are the critical distances that we have to take in account when dealing with noise problems. So if we said an aperture with this length is able to show the same behavior of a half-wavelength dipole. When this electric field vector is oriented perpendicularly in relation to the slit, the shielding attenuation at the corresponding frequency is about 0 dBs. Normally, easy way to try to solve this is to have, when we need to have a big aperture, we can divide it in smaller apertures, but at the end, also this distance is becoming critical. Because then between these points, we have a connection. The antenna is not that good as this one, but still we can have this kind of problems. For a two-dimensional breadboard, we have an influence also of the holes on a single row, and also, as we said, on diagonal. This is the number of holes we have, and the size of the holes is essential. When wanting to have a good ventilation for thermal issues, to avoid thermal issues, we need to optimize the area. The greatest area you can achieve with a shape is with a circle. That's why we use a circle normally. So in this case, we have to take in account this distance of each hole, the radius, and also the number of holes we have in the matrix. A calculation of the shielding attenuation depending of the apertures we have and the number of apertures can be seen with this formula. We will see a continuation. Here we have a table. This is the maximum. This is the maximum aperture size we can have in order to achieve at least 20 dBs of attenuation. So we have, for example, for 100 megas, we have 15 centimeters. You can see more. And here we have the relation we talked about, the number of holes. When we are increasing the number of holes, the shielding attenuation is decreasing. So if we have 2 holes, we have minus 3 dBs in attenuation. So our attenuation is worse, until about 80 holes that we have minus 19. So this is an overview for shielding solutions. You can divide it more or less by housing applications, PCB applications, and this is magnetic shielding that are special materials. We will talk later. So here we can see cabinets that are like a Faraday cage, earthing clips, conductive govens and covers, also copper tapes, aluminum tapes, contact fingers, and so on. So on joints, as we said before, we need to have apertures for buttons, or we need to have a cover to be able to open our device. So all these parts are not totally perfect. If we take a close side with a microscope, we can see that the surface is not regular. So in these cases, we are having these slots. With these slots, we are having the same issue we were explaining before. How can we improve this or this connection? We can use conductive gaskets or spring contact strips. If we place them in the middle, as we can see here, depending of the shape and geometry, we can achieve a better transfer of power between this side and this side. With this, we are avoiding the antenna effect. These parts are normally consisted on a foam material surrounded with a fabric that is depending of the material you can choose, nickel, copper, or aluminum. Usually they come with adhesive tape on a side for an easy placing. We can help to achieve the enclosure with a device protection of IP54 against water. So this is against water splashing and things like this, and there's also certification of fire protection in railway applications. We have also, it's possible to have this kind of gaskets with with in an elastomer way that are conductive. So to depending of the application, we can choose one or the other. An important thing to have in account is the matching of or the pairings of material. If we have an aluminum enclosure, it's important to use an aluminum gasket. It's possible if we go back, it's possible to select the material that is covering the foam in the gasket. We need to have this in account, as we said, is important in order to avoid corrosion problems. We can see here, we can see some matchings. As an example, if we have a tin enclosure, it's better to use nickel copper gaskets than aluminum gaskets. This is an issue with the galvanic corrosion, is called. And we need to have this in account in order to have a material that can or an enclosure that can withstand for more time and is stronger design. Then another kind of solution is the contact springs. This case, the concept is the same as the gaskets. So we need to have a very low impedance connection in order to have good transfer of power here. This can be seen most of the times, many times in anechoic chambers and things like this on the doors. This is a nice solution when you have to open and close the cover in the doors because they are flexible. They are also more, they are stronger materials than the gaskets. So with environmentally rough applications, is many times it's better to use this kind of materials. Normally, also it's nice to say that they are composed normally by a base material and with a plating. Then on cables, we have this kind of covers. They're conductive guban strips or covers for the cables. It's important to have wood connections at the ends of the cable, and it's important to avoid this kind of problem of connections. These are called pigtails, and what you are creating here when you are connecting the cable like this is connecting the shielding of the cable to the housing, for example, or to a PCB. This is called pigtail because this is creating an antenna directly on your ending connection. So it's important to have a 360 degrees connection, and this can be achieved by the using of this kind of clips. By having this, we're avoiding the pigtail problem. On flat wire cables, we can use this kind of tapes, either aluminum, copper tape, or conductive fabric. Also, sometimes you can use as a filter these magnetic materials that we'll talk about later, because with their properties, they are able to absorb the noise that is conducted on these parts. But basically, for the shielding of the cables connected on both ends, we can use these tapes. Also, for the connections at the end, it's important to have wood connectors to have a very nice connection between the shielding, then the connector, and then the housing. That's why many times also it's common to see stamped gaskets here placed on the connector. So in this way, the connector makes full contact and very low impedance contact with the housing. We have also this kind of filter adapters. They are composed by a low pass filter inside by capacitors, and they help filtering the high frequency noise on cables. Then if we go to board level shielding, we have the shielding cabinets. As we said before, these act like a Faraday cage. So they are 5-sided Faraday cage, and the 6 side is the copper or the ground plane or return plane of our PCB. With this, it's really easy to contain the noise coming out of an IC or to protect sensible parts of your connections or your PCBs, as are RF stages and 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 different several sensible parts or sensitive parts of our design. The normal solution we can find are one or two pieces cabinet like these ones, and also there is a possibility of using soldered clips. In this way, you can solder the clips on your PCB, and then you can plug you can make your cabinet pluggable. We can see internal compartments also to isolate different parts of the circuits, so they don't interfere with each other. And as we can see here, we can see a frame. This is for the two pieces solution. This frame is made for stabilization of the part and also to provide a point of pick and placing. We have also the do-it-yourself shielding cabinet. This is a metal foil that can be is foldable and can be cuttable. You can combine it also with the clips. This is a very good solution for especially for prototyping. So you can change the shape of your own cabinet, and you can do it on your lab in a very easy and fast way. This is the magnetic shielding we're talking about. These materials are composed with a ferromagnetic material, so they're able either to reflect or absorb the electromagnetic fields. Applications of these materials are, for example, when you have two PCBs and you have one PCB is interfering with the other one, so you can cause malfunctions. You can place this kind of materials to contain this noise and prevent this noise to affect the other PCB. Also, when we have an enclosure, we have resonances inside. The noise is created by this circuit, for example. And if you place anywhere on the housing this kind of materials, they are able to absorb the noise. So every time the noise is rebounding around inside the enclosure, this material is absorbing the noise. So at the end, it takes the noise to zero. An important property of this material is the permeability. This is what we were talking before about. They have a direct relation to the reflection or absorption ability of the material. So we can divide permeability into mu prime and mu2 prime. We can say that mu prime is representing the reflecting ability of the material, and mu2 prime is representing the absorption ability. So depending on your application, you need to be able to choose one material or the other, depending on what you want and the kind of effect you want to have at the end. Here we have some graphs about transmission attenuation. So this is the way of measuring it. We have a microstrip line. So we have a low impedance connection, 50 ohms microstrip line, and we place the material on the top. This shows the filtering ability of the material, as we can see here. This can be used also on flat wire, on flat cables. So this is the attenuation achieved. So for example, we can see between 2 gigas and 4 gigas, even with some of them, we can achieve more than 40 dBs of attenuation. This is directly filtering of the traces, data bus, CAN bus, or some parts of the PCB. Here we have the influence of the thickness of the material. So if we say this is exactly the same kind of material, but with different thickness, and we can see that if we choose thicker materials, we're improving the attenuation, but also we are moving the attenuation effect to lower frequencies. And we have, for communication standards, it's important to have these kind of materials also. They work by reflecting the field in protecting the device, as we will see in the following slides. For these materials, it's important to have a very good mu prime or reflection. So because we don't want to lose the power of the signal that we are transmitting, either if it is wireless power transfer or NFC RFID connections. So we want a very high reflection ability of the material and low absorption in order to not to have losses. So for frequencies of wireless power, these two materials are really good. We have high reflection, almost zero losses. The same for NFC RFID. A big problem in these kind of systems like wireless power and NFC is that you have normally the enclosure or metallic surface close to them. What happened with this issue is that the main frequency when this metal surface is absorbing the signal is creating an opposite field, and this opposite field is shifting the frequency to higher frequencies. So when we place the shield, these kind of materials, we can take back the frequency to the original one. In this way, the communication is not existing because the receiver is expecting this frequency. And here we can solve the issue with this material. This is a simulation result of wireless power connection or wireless power transmission. Here we don't have any kind of material protecting the system. So we have all this radiation coming out of between the receiver and transceiver. And here we have placed these materials. They are concentrating the fields, so the transmitted power is higher, and also we are protecting closer devices or parts of our circuit from this radiation. This is a new material that is a mixed between a thermal interface material and one of the materials before. It is able to conduct the heat through it as a thermal gap filler, for example, and at the same time it has electromagnetic properties, so it is able to avoid radiation. Heatsinks are many times an issue with these topics because they can act as an antennas. When they act as an antenna, they can create parasitic capacitance between the heatsink and the ground plane. So by using these materials, we're avoiding both problems. We are solving the thermal issue and the electromagnetic issue. So on board level shielding, also for grounding, we can use contact springs. These contact springs are low impedance connections, so we can use them for either ground plane sharing between PCBs or power sharing, also for RF connections, we'll see later. And here you can see normally the better the most connections you have, the better for the low impedance connection. So these are flexible. So when you place on a PCB, then you can make contact directly with the other PCB, and you have a very good low impedance connection. They are normally made of copper beryllium or phosphor bronze with a plating. The second one is better for power transmission. We have these ones that are also a new kind that they have a compression security system in order to avoid elasticity problems or overcompression. For RF connections, they are very suitable also because as they are low impedance and they can act in several directions, they are nice to have for modules of antennas or different RF stages between two PCBs. Another kind of material we can use here are the solderable gaskets. They are for the same applications as the contact springs, and but they are made in the same way as a gasket. They can be solderable, fully solderable on an oven, and they have also very low resistance over compression. Finally, in grounding is for low distances grounding and mechanical groundings. We have the grounding strips that can be combined with the spacers, and also copper tapes can be used in this way. The thing here is to have again low impedance on the connection to ground in order to avoid pigtails. These cables are twisted and are prepared to have designed to be low impedance connections. These are suitable mainly for low frequency connections as on power applications and things like this. So now, if you have any questions, I think Eleni will intervene. Thank you all for listening, and I hope you enjoyed.
Thank you, Antonio, for this great webinar. Now we would like to turn our attention to your questions, and we will wait a little while until some questions have come in. In the meantime, I would also once again like to draw your attention to the fact that you will be able to watch the recording of today's webinar once again a few days later on our website, and you will also get the PDF with all the sheets from the webinar in a separate email. Send it from us once again. So let's check the questions. So first question for you, Antonio. Why is it important to know the permeability behavior of a magnetic material?
So as we said, if we go to the slide, it's important to know where the material is acting as a reflection and when it's acting as an absorption, especially for communication applications. Because you don't want, when you are using it on wireless power or NFC connection, you don't want it to have a very low rate of losses. If the losses of the material that material causes is very high on this frequency, then it is absorbing the mixed signal of the communication, and you are making the communication worse.
Thank you for this. I will just check the next questions that came in. So the next question: what is the compression security system for the contact springs?
So this system is designed, this one is in order to provide a maximum point, when like mechanical point where you cannot compress it anymore. This is to avoid elasticity problems, as we said before. And normally when you overcompress a contact finger, what happens is that can break, or it can break, or it can when you are taking out the cover, for example, you have a cover and a contact finger in the middle. If you overcompress it and you take out the cover, then the contact finger doesn't come back to the original shape. With this kind of mechanical products and these mechanical solutions and systems, it is possible to avoid this kind of problems.
Okay, I've just picked up one of the next questions. It is it possible to modify the shape of a cabinet?
Yeah, let me go to the slide. So basically, the cabinets can be customized in many ways. As we said, it is possible to customize them with internal compartments, also with apertures. If you have, for example, a part of a device that you need to include a button or a small button or a testing point, it's possible to create holes only on one part. Also, the shape is possible to be customized to have bigger apertures on the side to take out a cable, or also the pins can be customized to have a better space or greater spaces between the pins to let the traces to go outside. So yeah, it's possible to customize it in many ways. Also, the material is possible to be customized depending on the frequency applications and the environmental roughness of the application.
Okay. I see that we only have one last question left. It is, why do we need to have an account the compatibility of the materials for selecting gaskets, contact springs, etc.?
So this is basically related with galvanic corrosion. When we have the very different materials, the materials can be classified. I think I'm gonna find. I will explain it anyways. The materials can be classified into cathodic materials and anodic materials. If we have two materials that are very different in this way, then we have a transfer of power between these two. This transfer of power can destroy part of one of the materials, and this is getting destroyed with the time. If we don't have a very good galvanic compatibility, this problem is caused. And when we have this problem, and a long time term, we are creating this kind of issues of destroying one of the materials.
Thank you. Okay, there's still one more question that just came in. It's a question concerning shielding magnetic field caused by a coil. Which core material of the coil would be effective to shield harmonics, not fundamental frequency?
So if I understand correctly the question, if we have a coil and it's working on certain frequency, and if you are referring to the internal material, then this is taken in account in the design, and normally it's not to avoid the it's not to provide shielding, it's to provide more power storing or things like this. But if you want to use shielding materials on the side or to erase these kind of problems, then you have to go again to the permeability values of the material. If we have this core on this coil that is working at let's say 1 mega, it's important to have a material that is that has or that has reflection or absorption capabilities in the frequencies you want. So in the case you want to raise the harmonics, if you have the main frequency at 1 mega, you need to have good absorption in frequencies higher than 1 mega. So you are not affecting the communication system and you are erasing the harmonics.
Thank you. So was our last question. If you still have any questions left, don't hesitate to contact us directly via isis-webinar at we-online.com. We will also answer your questions via email or contact you directly. And as I said already, you will receive all the PDF slides and the link to the presentation and the recording once again. And at this case, we want to thank you for your attention and see you next time. Bye bye.